Welcome, student, to beginning of the definition of derivative. In order to talk about derivative, we need to start with reminding ourselves what is the rate of change of a function. So, the average rate of change of a function y equal f of x from x equal 1 to x equal b is given by this formula. I will write this formula and then we will discuss what it means. The average rate of change from x equal a to b, it is f of b minus f of a divided by b minus a. That's the average rate of change. Does this formula remind you of something? Well, let me just write it down in a different way. Remember, b is the value for x. So x2, x1. So this will be y2, y1. Does it remind you y2 minus y1 divided by x2 minus x1? You are right. This is the slope of the line that joining f of a with f of b. This line is not the function. This line, we call it secant line. You see the line in purple is the secant line. It has a slope, and the slope is the average rate of change. The function itself could go as a curved, but if we just join those 2 points by a line, this line would be called the secant line, and the slope of the secant line is what we call it the average rate of change. And that's the first thing we learned now, is that the average rate of change is the slope of the secant line. It's given by y2 minus y1, x2 minus x1. Let's see some examples. Example number 1. Find the average rate of change, which again, it means slope of secant line, which means y2 minus y1 divided by x2 minus x1. That would give me the answer. So the average rate of change equal f of b, so f of 2 minus f of 1 divided by 2 minus 1. 2 minus 1 is 1. How much f of 2? F of 2 is 16. How much f of 1? Just plug in 1 here and 1 here. It will be just 10. So the answer will be just 6. Next example. What is the average rate of change? Equal to, it would be f of 1.1 minus f of 0.9 divided by 1.1 minus 0.9. Now, if you do this in the calculator, the answer would be just 5. So that's the average rate of change, which means for every increase of 1 unit in the x-axis, the y-axis will increase by 6 units. Similarly here, for every increase of 1 unit, the average increase in the y-axis would be 5. Now, why do we need rate of change? How we will use rate of change? We will use it to say what is the derivative exactly. Now, for the derivative, we will not have this one here. We'll just have 1x, and we want to see what's the rate of change if we just increase a by 1 unit. And that's exactly what will be the idea of the derivative. First of all, instead of using a and b, I will use x and z. Now, again, if we take the secant line, which is the line joining f of x with f of z, those 2 points, I will compare it with another line. We call it the tangent line, which is the line that only passes through the point b and only touching the function at b. So it's like just touch. The tangent line cannot be like this. It cannot go like this. Why? Because it's touched the function in 2 places. We don't want this. It cannot go exactly at this one because the function will be cut. We just want barely to touch the function. So we have 2 lines, secant line, tangent line. okay? Our focus will be here. And what is our focus exactly? It is to find the slope m of the tangent line, which we will call it later the derivative. So the slope of the tangent line, it's called the derivative. Now, how do we find the slope while we have only 1 point? That's difficult. We need 2 points in order to find the slope y2 minus y1, x2 minus x1. Well, the idea is a bit very clever idea we can do. Can you see the slope of the secant line? Imagine I start moving a q step by step. I cancel this q and I create a new line. And then I remove a q, I get another line. And then I remove q, I get another line. Those lines are getting closer and closer to the tangent line. So if I take the limit q goes to b, which means z close to x, I will get this slope easily. So the idea is to find the slope mq of the secant line and then start moving q closer and closer and closer and closer to the point P. That means my tangent line, the one in red, will be just the limit of z go to x of course, this will be very easy. This is f of z, y2 minus y1, x2 minus x1, and that's the derivative. So what we have learned is the derivative is the slope of the tangent line. How do we find the derivative as limit? This is the formula to find it as limit. The derivative is pronounced as f prime of x. And that's what we reach by the derivative. Of course, this is a bit complicated, especially later on when we do examples. The denominator is a little bit too complicated. So what we will do is we will use this formula, which is the same as the previous formula, except instead of writing z, I will write x plus h. So down here I have only one thing, which we call it h. And this is the definition of the derivative. Most of the examples we will use this one. Some examples you can use this one, it's up to you, but this one will be very, very handy in most of the examples. So this one you need to memorize. Now, sometimes it will tell you find derivative. Sometimes it will tell you find the slope of the tangent line. They are the same. Sometimes it will ask you to find the instantaneous rate of change. It is derivative. So instantaneous, not average, instantaneous rate of change is derivative. Slope of the tangent line, again, it is derivative. And that's what exactly derivative means. What we will do next is we will solve example in finding derivative